Welcome back. In the last class, we discussed about the strongly coupled spin system, worked out quantum mechanically what are the energy levels and the frequency of the transitions. And of course, before that, we also worked out what are the energy of transitions and quantum mechanically eigenvalues and transition frequencies worked out for weakly coupled two spin case, which was AX, and then extended to AB. One important thing we also said, in the AX case, we consider the situation J is equal to 0 and consider the situation J not equal to 0. When J is not equal to 0, we have off diagonal element coming into the picture, which is equal to JAX. We saw that half JAX was there, and then we also saw that JAX, that when you take the eigenvalues into account, energy level of the transitions, we thought when chemical shift separation is quite large, that term can be JAX can be ignored. So, we got all the four energy of the four energy states, and then got the frequency of the transitions and found out from the center of the chemical shift of each of the spins, coupled spins, let us say A and X. Let us say I consider A. There will be two transitions which are separated by half JX, one to the right and one to the left, same in the case of X spin. The interseries was same. Whereas in the case of the AB, it is not like that, because we have to consider JAB term also in the energy level E2 and E3, because chemical shift separation is comparable to JAB in this case, and we showed that outer two transitions of the four lines give rise to J coupling irrespective of the strength of the coupling, and central two transitions you take the frequency separation, take the frequency separation of the outer two transitions, multiply these two and take the square root of that, what you are going to get is the chemical shift difference A and B. So, in the strongly coupled case, they are not spectra amenable to first order analysis, and you get only the chemical shift difference, that is what I said. And the intensities are not exactly equal intensities like AX case. Here you are going to get different spectrum, that is what we are going to see today. You look at this one today. What we are seeing is the intensity of the AB spectrum, and I am written a stick plot of a hypothetical AB spectrum. It is a stick plot. Now, we see two transitions I1 and I4, they are of equal intensity, and there are two transitions at the center, these two are of equal intensity. Unlike in the AX case, they are not, all four are not of equal intensity, and we worked out also I1 equal to I4, I2 is equal to I3, and we found out this chemical shift separation, this 2C is equal to 2C minus J, and we found out frequency separation or delta AB is nothing but frequency separation between this and this and this and this, multiply these two and take a square root of that. And JAB is always the outer frequency separation of the outer two transitions. This is a typical AB spectrum. Remember, outer lines are of always weaker intensity compared to central transitions. Of course, in the realistic case, what happens is these two lines will not be exactly equal, they will be like this. Some may be slightly, it is tending toward this maybe. That shows it is called a roof effect, which tells you the direction in which these two spins are coupled. Anyway, that is not important, which we discussed in the first course, in the elementary course. So, in this case, as of course, complete analysis is not possible without quantum mechanics. In a single, of course, in the AB cases somehow we can get the information except individual chemical shifts. But if you go to higher spins, more than 2, 3 spins coupled, 4 spins coupled, it is impossible to get without getting into quantum mechanics and also numerical simulation. This quantum mechanical analysis by this way is not pretty simple. Beyond 3 interacting spins, it is going to be very tough. You have to resort to numerical analysis using computers. Okay. So, now the ratio of the peak intensities also we can consider, that it can be easily obtained by taking into account the frequency separation. Nu 1 minus nu 4, you take ratio of the frequency separation between 1 and 4 and 2 and 3, this correspond to intensity ratio I2 by I1 and IR equal to I3 by A1. So, if I want to take the intensity of these two peak, intensity ratio I2 by central one of the central lines with one of the outermost lines next to each other, adjacent lines if you consider, that is nothing but this frequency separation divided by this frequency separation. That gives you ratio of the intensity of the peaks. See, please remember, this is J, and if I have to get this one, nu 2 minus nu 3 is you have to consider nu J over J is equal to, oh no, it is not in this case, it is 1 by 1 and 4. You have to consider the separation of 1 and 4 and 2 and 3. If you take the ratio, you will get ratio between this and this or this and this. Okay. AB system gives centrosymmetric 4 lines. It is symmetric with respect to the center. All peaks are not of same intensity. You understand that? Two central peaks are of identical intensity. Two outer peaks are of identical intensity. That is what we observed in a hypothetical stick plot. And regardless of the strength of the coupling, outer two lines always gives corresponding J coupling. For example, I consider the case like this. This gives me J. Whatever, if the coupling becomes slightly small, let us say, does not matter. Nevertheless, I get only, I take the outer lines separation, consecutive outer lines, two outer lines, you get the J coupling. Whatever will be the strength of the coupling, you get separation with the two outer corresponding consecutive outer lines gives rise to J coupling. And as I told you, first order analysis is not possible in strongly coupled cases. You can get only difference of the chemical shifts, and J coupling of course we can obtain. And sign of the couplings will not affect the spectrum. This we have been telling even in the first class also, even in the previous course, even in this course earlier 1 or 2 classes. I told you in the one dimensional NMR spectrum, the sign of the coupling do not influence the spectral pattern. Does not matter you take chemical shift, let us say I will have a AX spin system with a coupling constant of 10 hertz positive. You make it 10 hertz negative, this line will become here, this line will come here. Similarly, this will come here, this will come here. Pattern remains same. You will not find the difference at all. So that is why I said one dimensional NMR spectrum will not give the information about the sign of the coupling. Here also, as I said, again I am repeating, the sign of JAB does not influence the spectral pattern. Okay. So AB has now two limiting cases. One, what happens if the chemical shift separation becomes very, very large? It is very simple. We already discussed delta AB, chemical shift separation between these two become very, very larger than J. This is AX case. It will become an AX. Now go to a situation, delta AB becomes very, very, very small compared to J, or almost delta AB will become equal to 0. I will say there is no chemical shift difference at all. Then what will happen? It is called A2 spin system. So this is the important thing you should remember when the chemical shift separation in the limiting example of this case, when J coupling is 0, we are going to get AB as A2. So this is the limiting example of AB. In one case it can become AX, in other case it can become A2. This is A2. So depending upon the strength of the coupling and the chemical shifts. So the limiting case of AB equal to, when delta nu is equal to 0, what is going to happen? Very interesting case, when chemical shift difference becomes 0, two outer lines, the two inner lines will collapse, two outer lines will disappear. Very interesting. Now you have a 4 lines here. These lines, as you keep on becoming stronger and stronger, J coupling, chemical shift difference becomes smaller and smaller, then what will happen? You will see this outer lines keeps going away, far away from this thing with reduced intensity. And when it becomes very, very strongly coupled, outer lines almost become negligible and disappears. When it becomes exactly A2, this will disappear and these two chemical shift overlap. These two peaks overlap. So in A2 case is a special example of AB where you do not get 4 peaks, you get only 2 peaks. Very interesting how it happens. I am going to explain to you now, you will see. AX and AB spin system gives 4 lines, okay, whereas AB is going to give you 2 lines. I am sorry, A2 is going to only gives you 2 lines. AB and AX will give you 4 lines. We saw that. We worked out the eigenvalues and the energy of the transitions, everything. But A2 gives only 2 lines. What does it mean? Why it happens? We will see. Again we can work out quantum mechanically, because then we can work out n number of spin system. I wanted to give you only an idea how to quantum mechanically work out coupled spin system. We have taken 2 examples, AX and AB, that is enough. No need to go further for 3 spin, 4 spin or strongly coupled, weakly coupled, etc. But simply remember A2 gives rise to 2 peaks and transition from AB to A2 is going to be continuous. It is like this. I have a AX spin system, as you know, well separated 2 lines for A and 2 lines for X, well separated 2 doublets. Now chemical shift separation is quite larger here. Now make a situation chemical shift becomes smaller and smaller. chemical shift separation, then outer line keeps moving away. So inner peaks start moving inside, only outer peaks goes out, again it goes further out, and this becomes further in, keeps inner peaks keeps coming closer and closer, outer peaks keeps going far away from each other, and then intensity of this keeps on reducing. Outer peak intensity of these peaks will overlap, keep increasing, and come to a situation when delta is nu equal to 0, this will disappear, there are no outer peaks here, only these two will overlap and gives us a single peak. This is a transition which goes from AX to AB, is always smooth, keeps going like this. Okay. Of course, AX to AB also we can think of like this. I mean different case, when delta nu by j equal to 0, then it is when A2 spin system, AX will become AB. We went from AB to A2. Now we can go to AB, AX becomes AB, and further when they become stronger and strongly coupled, you can see that our outer peak become very, very small in intensity. Okay. So this is the way we can understand AX AB spin system. Now we will go to A2 spin system. Without going into the rigorous mathematics, I will show you. This is a situation we have coupling between these two is AA, it is present. You may not see that. A2 is a situation where two spins are very, very strongly coupled, because there is no chemical shift difference at all, both are identical. Okay. And delta A1 is equal to delta A2, both chemical shifts are same. So delta is 0, and A1 coupling JA1 to A2 is not 0. See, in a magnetically equivalent spin case, I told you when they are coupled, magnetically equivalent spins are coupled, there exists J coupling. Remember, there exists J coupling, but you do not see in the spectrum, they are not reflected in the spectrum. Similarly, in the case of homonuclear A2, there exists a J coupling between two A spins, but you may not be able to see that. Similarly, heteronuclear A2 is not possible, because the chemical shift separation is quite large. Okay. So homonuclear A2 is present, and this is what happens. Without going to the rigorous mathematics, I will show you. In the A2 case, we have two transitions, four energy levels, beta beta and alpha alpha for two spins, 1 and 2, and there are two other transitions. Remember, in earlier case weakly coupled, it was alpha beta and beta alpha, and I told you in the AB case we can also write like this, cos alpha into alpha, cos of alpha beta I wrote, and plus sin of beta alpha. In other case, if it was negative I wrote, but anyway rigorously I did not write work out everything, but this is what it turns out to be there. See, in this case, these two energy states can be written as 1 of square root of 2 into alpha 1 beta 2 plus beta 1 alpha 2, 1 of square root of 2 alpha 1 beta 2 minus beta 1 of alpha 2. These are the two energy states. Now, one interesting thing you should observe, this is a symmetric state. Symmetric state means if you interchange this from alpha beta to beta alpha, the sign will not change. Whereas this is antisymmetric state, if you interchange this alpha beta, you make it beta alpha, sign will change. This is an antisymmetric state, these are all called symmetric states. There are 3 symmetric states and 1 antisymmetric state in A2 coupled spin system. One important rule you should understand, transition between symmetric to antisymmetric are forbidden, it is not allowed. Only transition between symmetric states are allowed, or only between antisymmetric states are allowed. No transition between symmetric to antisymmetric are allowed. That is one of the rule. You should remember that. As a consequence, only these transitions are allowed. Now I am considering a situation JAA is equal to 0. When JAA is equal to 0, a very interesting thing is going to happen. Please remember, when JAA is equal to 0, so JAA when it is equal to 0, what is going to happen is, we are considering only situation, these two energy transitions are allowed, whereas transition between this to this are not allowed. So, and these transition frequencies are same, this is same, and this transition frequency, this transition frequency are same, identical, and this is not allowed. So, A2 spin system, you can consider a situation again, coupling could be 0, they are magnetically equivalent, does not mean coupling is 0 or coupling need not be present. Coupling can be present, coupling can be not be present also, it could be 0 or non-zero. Now I consider situation JAA is equal to 0, then I am going to see, I am telling you this is not allowed, only two transitions are allowed between three symmetric states are there, between this to this is allowed and between this to this is allowed. They are identical frequencies. As a consequence, what will happen? It will overlap. That is why in the A2 spin system you are going to get only single frequency, single peak with two frequencies identical overlapped. Unlike AX and AB, where you get 4 transitions when 2 spins are coupled, only in the A2 case you get only single transition, which is nothing but 2 frequencies which are overlapped. You do not get 4 frequencies in A2 case. Now what happens if a situation JAA is not 0? It could be positive or negative, it does not matter. I consider situation JAA not 0, greater than 0. Now what will happen is all the three symmetrical states are lifted up by J by 4. You can work out rigorously with mathematics from what I showed you. Simply you know the wave functions, you know the energy eigenstate beta beta is there, and this is alpha beta plus beta alpha by root 2, and this is alpha beta minus beta alpha by root 2, and you know the Hamiltonian for H0 and H1. You can write down and work it out very easily, simple arithmetic. So I did not work out, but already I have shown you for 2 cases. But remember, in this case what will happen is all the 3 symmetric states are lifted up by J by 4. On the other hand, the antisymmetric case, antisymmetric transition is lifted down, down by minus 3J by 4. These 3 will go up, this will come down, antisymmetric state. Okay, that is what is going to happen. So, but still what is happening, this transition is not allowed. Okay. So, as a consequence what is going to happen? Again you are going to get these transition frequencies which are identical, because all the 3 energy states are shifted up by same amount A by 4. So, the difference remains same. As a consequence, whether J coupling is 0 or non-zero, in the A2 coupled spin system you always get 2 transitions of identical frequencies, and both the cases the transition from symmetric to antisymmetric are forbidden, not allowed. As a consequence, in the A2 case you always get single frequency, which is nothing but 2 peaks overlapped. Now what happens if I can take the example of a 3 coupled spin system? What do we get out of it? Should we analyze this? Remember, it is going to be a very terrible job for you. There are various possible combinations you can think of in 3 cases. For example, all the 3 can be magnetically equivalent, A3. 2 can be strongly coupled, magnetically equivalent A2, and these two together with the third spin can be strongly coupled, but they are not equivalent. Or similarly 2 can be chemically equivalent and both are strongly coupled to third spin. This is possible, and 2 are strongly coupled and both of them are weakly coupled to the third one. 2 are magnetically equivalent, very strongly coupled A2, and both are weakly coupled to third one, and all the 3 are weakly coupled non-equivalent. Both are strongly coupled and weakly coupled to the third one, and all the 3 can be weakly coupled. Varieties of possible combinations you can think of in spin nomenclature. This is remaining only for 3 spin. Imagine you go to 4 spins and 5 spin, you get umpteen number of possibilities you can think of. For each of them, if you want to work out quantum mechanically, it is going to take you all your lifetime time. It is not easy. It will take enormous amount of time. It is not difficult. You can keep working out pages and pages and pages of calculations you do to get the eigenvalues and eigenfunctions. So it is not worthwhile doing that. But anyway, many in the olden days people have already worked out some of the cases. It is available in the books. But we have shown for 2 spins, AX, AB and A2. Now we will see simple case AMX without going into rigorous mathematics, how the AMX works. AMX 3 weakly coupled, chemical shoots are far away separated, delta A is very much greater than delta M, which is very much greater than delta X. This is the condition. And there exists a coupling between A and M, there exists a coupling between A and X, there exists a coupling between M and X. There are 3 couplings and 3 different chemical shoots, and all are weakly coupled because we are representing by 3 different alphabets in the Roman alphabets which are far away separated. So it is a 3 weakly coupled AMX spin system. Pretty easy to analyze, that is why I took it. If you go back to ABC here, it is much difficult. So that is why I took the simplest one to show you in the A3 case. Write down the Hamiltonian again. Now this is the H0, only Zeeman term is taking into account, And now this is the J coupling term. Take the J coupling term, very right. Same what we wrote, it is a general term. Previous case we took 2 spins, now we have to take 3 spins. How do we take 3 spins? Now chemical sheet of 1 interaction, it's a Zeeman interaction with external magnetic field. Chemical sheet of 2 with its Zeeman interaction of the chemical sheet of Zeeman interaction of spin 3, Zeeman interaction of spin 1, Zeeman interaction of spin 2, Zeeman interaction of spin 3. Then J12 I1 I2, J13 I1 I3, J23 I2 I3. Remember, each of these terms you have to expand in terms of Ix, Iy, Iz, and then construct the Hamiltonian. And there are 8 product functions. Remember, alpha alpha alpha, alpha alpha beta, beta alpha beta alpha, beta alpha alpha, and these 3, and finally beta beta beta. Various combination you can think of. Orientation, all the 3 can be alpha, all the 3 can be beta, these 2 can be alpha, and this can be beta. Like that, all combinations you can think of. There are 8 possible product functions. That is why I said for n interacting spin there are 2 to the power of n product functions. So in the 2 squared, 2 spins we had 4, 3 spin we have 8, go to 4 spin we have 16 product functions. Imagine 16 into 16, that is the big matrix you have to analyze. Here already 8 into 8, 64 by 64 matrix, 8 into 8 is 64, 64 elements will be there, 8 by 8 matrix you have to analyze, unlike 4 by 4. 16 by 16 is another big matrix for 4 spins. So we have to analyze this 8 by 8 matrix. It is very difficult, all 64 elements. If you want to work out, you will have to work it out, for it to runs into tons and tons of pages for calculations for you. So we will not worry about it. We will see what are the eigenvalues and the transition frequencies in the simplest possible way. The wave functions are, as I told you, the product functions, especially in the weakly coupled case. You do not have to worry about alpha beta plus beta alpha by root 2, alpha beta minus beta alpha by root 2, which I said earlier case. Same here, if instead of AMX, if I make A3, you get symmetric, antisymmetric states, everything here. Since I am considering AMX weakly coupled, simply I wrote product functions, and Fz is the case. Total spin magnetic quantum number for this energy state is 3 by 2, because we have all the 3 spins up, alpha, 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 half, 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 it will become 3 by 2. And now energy state 2 plus half, 2 up and 1 down, alpha, alpha, half of, and 1 is beta, minus of, the sum turns out to be plus of. Similarly, these 2 are the situation, sum turns out to be half. Here these 3, 2 up, 2 down and 1 up, sum is minus half, and all the 3 are down, sum is minus 3 by 2. And very easily energy states have been worked out. Very simple for us. Imagine it is not simple. If I have to work out again, I have to write down the calculate the energy, each elements of the matrix, find out which are 0, which are non-zero, and then you have to construct the energy state like this. So simplifying the work, first energy state is simple, nu A, nu M and nu X is there, all the 3 chemicals should divided by 2, and JAM, JAX, JMX by 4. Second energy state, AM and minus X by 2, JAM minus JX minus MX by 4. Like that, very easily all the 8 energy states are worked out. Now for all the 8 energy states, how many transitions you can obtain? Very simple. You find out what are the transitions which are allowed according to our selection rule. For the transition frequency, if you go for the AMX spin system, for state 1, transition between 4 and 1 is allowed, 6 to 2 is allowed, 7 to 3 and 8 to 5 are allowed. I mean, instead of state 1, I would say transition. That is easy to say. Instead of state means you may get confused with the energy state. So I will consider there are transitions. Transition 1 is between the transition states 4 and 1, which correspond to transition A spin. You understand? Now I consider transition 2. The transition 2 is between 6 and 2. It again corresponds to A spin, because the origin this one of the spin which is undergoing transition is for A spin. For example, alpha alpha alpha, beta alpha alpha, if I write, If the transition undergoes between alpha to beta, this corresponds to A spin. I can write it as A, M and X. So, here A spin is undergoing transition from alpha to beta or beta to alpha. So, this I call it as A transition. So, like that, if you can work out from the energy states, you can see transition from 4 to 1 or remaining these things, all these things. See, for example, 4 to 1 is A transition, 6 to 7 is 8 5. You can calculate yourself, you find out the difference between the transitions. The origin of the spin for all of them, transition which is undergoing is A. A spin is the one which is undergoing flipping. They are called A transitions. If you consider the energies other transitions 5, 6, 7 and 8, which is between 2 and 1, 5, 3, 6, 4, they all pertains to X transition, where the X spin is undergoing flipping from alpha to beta or beta to alpha. Again, these are the energy states from the difference of the eigenvalues. Now, go to a situation, remaining 4 transitions, they are all from 3 1, 5 2, 7 4, 8 6 states, and they all pertain to M transitions, where M spin is undergoing flipping from alpha to beta or beta to alpha. So, there are 3 product functions. Among the 3, any one of them can undergo flipping from alpha to beta or beta to alpha. If A spin is flipping from alpha to beta or beta to alpha, that corresponds to A transition. If M is flipping from alpha to beta or beta to alpha, that is M transition. Similarly, if X is flipping from alpha to beta or beta to alpha, that is X transition. So, AMX spin's case, you have got 12 transitions. 4 transitions correspond to A, 4 correspond to M and 4 correspond to X, and all of them you can find out the frequencies here. Very interesting thing you have to see here. Each spin is coupled to 2 other spin. You consider A, M and X. A is coupled to M, A is also coupled to X. Now, I consider A, M and X. M is coupled to A, M is also coupled to X. I consider A, M and X. A is coupled to X and M is also coupled to X. So, each spin is coupled to the remaining 2 spins. What is the type of spectrum you are going to get? 4 peaks you have got for each of them. But remember, in the AX case I told you, from the chemical sheet separation at the center of A, there are 2 peaks which are separated by half of JAX, one towards the plus JAX, other towards minus JAX. The separation gives JAX in the AX case. But in the AMS case, you are getting 4 peaks. Very easily extend the logic. For example, if I consider A is separated coupled to M and coupled to X. So, at the chemical sheet of A, I get from that I have got 2 peaks on either side, one correspond to JAX, other correspond to JAM. Very easy, exactly the same logic. I hope it is very clear for you to understand. If not, I hope if it is not clear for you, I will tell you very simply take one example and explain to you. I consider, let us say, chemical sheet of A. This is A spin. A spin is here. Now, I get 2 peaks here and 2 peaks here. You can see here from A chemical sheet plus A, there are 2 plus AM by 2, AX by 2 on either side, AM by 2 and AX by 2. Similarly, minus AM by 2 minus AX by 2 on either side. There are 2 peaks on either side of each chemical shift, which is nothing but half the J coupling of remaining 2 spins. So, now this is the passive spin, I am sorry, active spin I am seeing. It is giving rise to coupling with the passive spins. Each is going to be 2 lines on either side. One separation gives you one of the passive coupling, other separation gives you other passive coupling, not complete, half of the value. And if you take the separation for corresponding peaks, you are going to get both the couplings. So, energy level transitions very easily you can understand. This corresponds to X transition from plus 3 by 2 to minus 3 1 by 2. Here X is undergoing transition. Similarly, this is X is undergoing, here X is undergoing transition. So, there are 4 X transitions. Now, this is A transition, this is A transition, this is A transition. There are 4 A transitions. Okay. Now, next is M transition. This is M, this is M, this is M, and last is M. There are 4 M transitions, 4 A transition, and 4x transitions. And in a very interesting things is going to happen. For example, if there is a possibility these 3 can come to these 3, plus of to minus of allowed, because they changing the quantum number, the magnetic quantum number is plus 1 or minus 1. That is all the 3 spins are simultaneously changing, not one. In the previous example, in the previous slide I showed you only A spin is changing or M is changing, X is changing, 4 such transitions for each we saw. But in this case, for example, here all the 3 are simultaneously undergoing. That is why it is called a combination transition, where all the 3 spins flip simultaneously from alpha to beta, and this is the example where this transition is allowed. Similarly, this is also allowed. All the 3 are changing plus similarly this is also allowed. So, there are 3 combination transitions in this 3 spin case. In addition to 12 transitions, 4 for A, 4 for M and 4 for X, you are going to get 4A, 4M transition, 4X transition, plus 3 combination transitions will be there. So, there are 15 transitions for 3 coupled spin system, but interestingly in the weakly coupled case all the 3 combination transitions are not seen. They are almost 0 intensity, you will not see. But if you go to strongly coupled case, you will see that. But where do these combination transitions will occur? They come only at the sum or difference of the chemical shifts. You can find out from this table, from this energy level diagram which I have given you. You go back here and you can find out transition which I gave you, which I showed you. Then you will find out in the combination transition is probability, the only thing is all of them will come at the sum or difference of the chemical shifts. And because of that, combination transition contains no J information. See here, no J term coming, only nu A plus nu M minus nu A plus nu M plus nu X, sum of 2 chemical shifts of M and X minus chemical shift of nu A. That is all your, at that place you get one combination transition. Another combination transition you get chemical shift at the sum of chemical shift of A and M and minus of X. For example, one chemical shift is coming at 100, other is 200, other is 300, let us say. This is A, this is M and this is X. Now combination transitions, let us say one of them will come at chemical shift M and X 200 plus 300 500 minus nu A 100. So at 400 you will see one combination very weak intensity peak that correspond to one of these combination transitions. There is no information you get out of it except this, no J coupling. So very weak intensities you see only them in strong coupling case, strongly coupled spin systems, not in this case. So splitting example of for the AMX I am going to give you like this, a simple case where all the 3 couplings are positive in sign like this. So A can split with the M, give us a doublet, and it will give further split with X, gives a doublet of doublet. Similarly, M will couple with A, gives doublet, and couple with X gives doublet of doublet. X will couple with A, gives doublet, again couple with M and gives us a doublet of a doublet. So this gives rise to JAM, this gives rise to JAM, whereas this separation gives you JAX. Similarly, because M is coupled to A, this will give you JAM, this will give you JMX. So like that all coupling information can be obtained. But of course, I did not want to show you here. There is an example what happens if the couplings. See here I have taken the example, several conditions we can put. Nu A is greater than nu M, nu A greater than nu X. This is the pattern. Now also I can think of what happens if JAX greater than JAM, JMX greater than JAM. What happens if this is larger than this, larger than this? All combinations you can think of. Accordingly, the pattern of the spectrum changes. You can also think of what happens if one of the coupling is negative, other is positive, other 2 are positive, or 2 are negative, 1 is positive. All the 3 are negative, what will happen? Varieties of combination you can think of. Simply go back to this AMX case, work out with yourself in a stick plot, consider situation. Now 3 JAX is greater than JAMX and JAM I have taken. Make JAX very small compared to JAMX and JAM, or make one of the coupling 0. See how the pattern changes. In one case you get only 2 lines instead of 4 lines. These are the things, the splitting pattern can be easily understood by quantum mechanical analysis. So 3 spin case also it can be done. I did not explicitly do, but I showed you the procedure to do that. And in AMS case I told you we have get 4 for A, 4 for M and 4 for X transition, 12 transitions plus 3 combination transition at the sum and difference of the chemical shifts of A, M and X, which are very weak in intensity, are not seen, whereas they are seen in the strongly coupled case. So, with this I am going to stop here. Before that, I want to tell you, so far in the quantum mechanical analysis of the coupled spin system, we have discussed a lot. We started telling you how we can go ahead in making the analysis of the spectrum to get the chemical shifts and coupling constants for all the coupled spin system. What is this type of spectrum we get for weakly coupled? What is the type of spectrum we are going to get for strongly coupled spin system? We took the example of AX. We knew what are the wave functions. Wave functions are nothing but the product functions. We constructed the Hamiltonian, taking into account only the Zeeman interaction, considering J0, taking into account the J coupling present, which is non-zero. Then we constructed the Hamiltonian, and then use this, and we wanted to work out the eigenvalues. For that, we constructed a matrix, secular equation we got, worked out, and then each and every element of the matrix we had to work out. And I showed you for 2 spin case there are 4 by 4 matrix, 16 elements, and then out of which in the AX case, when J coupling is 0, we have only 4 diagonal elements, and we get 2 transitions for each A and X, which are overlapped with J is 0. When J is non-zero, we set 4 peaks, 2 for A and 2 for X, well separated with by JAX. And similarly for AB, I said 4 peaks are there, outer peaks of equal intensity, 2 central peaks of equal intensity. Outer peak gives rise to J coupling, central peak separation. If you take multiply by outer peak separation, multiply and then take this square root of that, we are going to get the chemical shift difference. I told you in the strongly coupled case there is no way you can get the chemical shift individually, you can get only difference of chemical shifts. So, and took the example of 3 spin weakly coupled and showed how the spectrum comes, how the combination transitions come, and what are the possible spin states, what are the possible nomenclature possible in 3 coupled case, and took the simplest of weakly coupled AMX and showed you how many peaks we get with a simply a stick plot, and also by transition for taking into account different energy state which has already been worked out. I did not explicitly work out that, but I took the thing from the table we worked out. So, with this I am going to stop this. So, quantum mechanical analysis of coupled spin system is complete. In the next class we go to a different topic. Thank you.